Yeah, we figure out the sound. So now I have my headphone. I'm not going to mute myself like globally, just not even mute myself. So how does it sound on YouTube? It is good. Maybe I should speak, or someone should. Some. Right. Yeah. Wait. Okay. So you didn't hear yourself except for me. All right. Okay. Right. So that's. I'm trying. Yeah. Okay. It's not gonna fly. I don't think so. Uh. Yeah, you are. Uh. Yeah.
Oh,
All right. We tried this before, and
you're muted, Csaba.
so we tried this before, and okay, no, I remember. Somehow this is unexpected, because you would think that this is only capturing the output, but somehow, all right. So in YouTube, the desktop audio, like through this mixer, is the sound that to be produced, and the desktop audio is captured by this guy, and so it doesn't go to YouTube. So rather than like it's a
Right.
split and it goes everywhere, this guy just captures it, and then YouTube is not getting it. There is no desktop audio after I turn this on. So thank you for
I think
this very clever design, Apple.
I think what you'd need to do is like unscrew the computer and get the wires that go into the speaker and like connect them up to your headphones, and then have a dedicated laptop that you can do this with.
I think that there is probably one more thing. Yeah, like this is a very good solution, Gellért. Should definitely
Thank you.
do this on the Corp laptop.
Yeah, the other one, should be under warranty, so you don't want to break that. So, of course.
And but seriously, I think that like this software mixer thing maybe can be reconfigured, but I'm not going to attempt to do that in the last 4 minutes. So
Yeah,
we just
anyhow, it
roll
sounds
with
good now.
the usual bad setup that we have, and
There's
sorry about
actually a
that.
bit less echo than normal. I don't know if you did anything, but
No,
okay,
I
well,
I can't hear any echo now, so that's
you
good.
can't hear any. No, okay.
No.
yeah,
So
no, over
normally
there on the stream, there's a different flavor of
Oh, I see.
echo. Yeah.
yeah. So the YouTube stream will have some echo, I think.
That's good, because I think it's worse for the speaker, because they get confused and they don't know what they're saying. Whereas I think if you're listening to echo, you can still kind of understand the sentences.
Oh, actually, I remember. So the first part of it is that even if I turn off my microphone in Google Meet, since I'm streaming to YouTube, the microphone is listening in the background as well.
Yeah, so like all the background noise, like the dogs barking
I
and
start
stuff,
to type,
makes it
then everyone would hear that I type. I'm like, wow, okay, that's pretty annoying. Yeah.
Yeah, that's not the best. But anyhow, it's good.
Hello, BG.
Hey.
Hello.
How is the summer?
At the moment it's very hot,
No.
but still going.
Hey
it?
man.
Don't you
Yeah,
have
same.
some
It's terribly
nice
hot.
breeze on the beach?
Yeah, we have some. Snorkeling every day.
Snorkeling? Wow.
Yeah. But eventually I have to work too, and that's difficult now.
Okay.
Yeah, the beach is nice but crowded here as well.
Here it's not okay. Yeah, it's crowded.
Is it
Compared to the
crowded?
usual,
Do you know?
but it's not comparable to Barcelona, so it's
relatively peaceful. Good.
How is Canada?
Well, we got a heat wave last week, and this week it's all rainy. I just hope the weekend is gonna get better. The heat wave was like really horrible. Like, I mean, it was fine for me, but it was quite high temperatures. In BC, they measured almost 50 Celsius.
Wow.
Wow.
50.
That's really extreme.
Wow, that's crazy.
Yeah.
I guess this was maybe the first time you used the AC in your car, right? Because otherwise you're like, why is it even in there?
Well, yeah, okay. It's more like the house ACs. Like we had this fight with Chonger about like what temperature to set the AC at, because he wants to cool down the house to the temperature of a fridge. In my opinion, I would prefer some warmer temperature, but yeah.
Was it just heat, or did it come with forest fires as well?
Oh, the fires are burning. It's pretty bad.
That's usual.
Yeah. It's not yet in Alberta that much. It's more like BC. I'm actually surprised about that. But maybe we got lucky and we got some rain, because this week it was raining on and off. So that's very helpful. But BC is like getting the worst of it. So I just hope that the smoke is not going to get here again. Like sometimes.
Yeah, it was hot.
Yeah, it can be really bad.
Well,
shall we?
Some fires.
Yeah.
Yeah, you're right. I think we should start.
Maybe you should start.
Yes, that's right. So did we decide who's introducing who, or how does it work?
I'm happy to introduce Gelért.
All right. Okay. So let's do that. Okay. So maybe I'm just gonna do the intro. So all right, let's get started then. Welcome everybody. Looking at the list of names, I think I can say welcome back everybody. So it's gonna be the usual recipe. We're gonna have a 50-minute talk by our speaker, followed by like roughly 10 minutes of official questions that go on the record. And then we're gonna stick around for like 30 more minutes to chat a lot more, get to the details, or ask the nastier questions. So stick around for that if you're interested in the juicy bits. It's important that you keep muted during the talk so we can hear Gellért and there's no interference or anything. And if you have any questions, just type them here in the chat. We're gonna pick out the most interesting questions and ask them to the speaker. And the same goes for YouTube. So if you're following the stream on YouTube, then just type your questions in there. I'm gonna try to channel some of those to the speaker. And I think that's everything. So I'm gonna pass it over to Csaba, who's gonna be introducing Gellért.
Right. So it's my great pleasure to have Gellért here, whom I known since quite a few years by now, and he finished his master's at Cambridge, and after that he joined DeepMind, and in DeepMind shortly after he started to work with our group and also with me, and he broke into this sphere of reinforcement learning theory with a bunch of new papers. He started a PhD recently at UCL, and he's just crushing it all. And so it's a great pleasure to have Gellért talking today here. So Gellért, stage is yours.
Cool, thank you. Thanks for the wonderful introduction. Okay, so I'm going to talk about tensorplan, which is a new, flexible, scalable, and provably efficient local planner for huge MDPs. Yeah, you can see the slides in the chat. Right, let's dive right in. Let's see. Okay, this is joint work with Csaba, Philip, Barnabás, Yasin, and Nan. And the link to the paper is right there. Okay, so a little table of contents for today's talk. I will first introduce the setup, which is large-scale planning under linear realizability of Q star, which is the optimal action value function, or V star, which is the optimal state value function. And then I will review some of the related recent results here, and then we'll consider one of the possible assumptions and look into why the approximate dynamic programming or bootstrapping kind of algorithms don't really work for that. And then I'll introduce a new method which we'll learn a little bit differently, and this is called tensorplan. You'll see why, so stay tuned for that. Okay, before we jump in, I just wanted to flash up this slide. This has a sort of a pure mathsy linear algebra riddle, and I think it's beautifully simple. So we're not going to talk about the solution to this, but I just wanted to flash it up in case you get bored of me talking. You can always come back to this if you take a screenshot right now. And of course, this was not solved by me. This was solved by an amazingly talented mathematician called Barnabás. Here, yeah, and I think it's very rare to have some sort of a pure mathsy kind of simple problem being the crux of such a like an RL kind of question. So, but you'll get a bit of a spoiler in 20 minutes about this. Okay, let's look into the introduction, which is like what our Markov decision process is and what is planning, and we'll set the problem up first. So a Markov decision process, or MDP, is this tuple of a set of states, a set of actions, a set of probabilities for transitions, some rewards, and a horizon capital H. So we're in the finite horizon episodic problem. And so this kind of represents an environment in which you can learn how to act. So for each state, let's say there are capital S states, and this is a finite number. By the way, this assumption of the state set being finite is just for simplicity. All the results we present today will hold for infinite state spaces as well. Okay, so you have a state space, and in each state you can perform one of the many actions. And when you perform an action, you will be transported to a next state according to some transition probabilities that will be given by P of S and A for state S and action A. And you also observe a reward, which has an expectation. It's stochastic, but it has an expectation of R of S and A. And there is also the assumption that these rewards will be bounded between 0 and 1. If you have a policy, which is a mapping from states to transition probabilities distribution on the actions, then you can calculate its value, which is the value of a policy is the expected reward we gather in H steps if we execute the policies according to the probabilities in the MDP, and then get to the next state and continue like that. And this is actually if we're indexing things by lowercase h, which means that in this case we only have capital H steps. So if we've performed 3 of those already, then the sum will go not to capital H, but capital H minus whatever the lowercase h is. And so we're summing up the rewards, taking the expectations, and that is going to be the value of a policy. And then, of course, we have the V star, which is the optimum, for the best policy, what is the value when we start from state S. And the objective is to find a policy that is, close to optimal, such that its value is going to be close to this V star. And then we collect the highest possible amount of reward, at least an expectation. But it turns out that to find this policy, it's actually enough to find the V star values themselves. Because if you know the V star values, of course, you can take the action that would maximize the reward plus the next state's V star values. And you can just act like that, and that will give you a policy that's optimal. So, it's kind of a central question to get the values of the V star, which is the optimal state value function. Because then you basically know everything there is to know about the MDP. Okay, to set up the local planning problem, here we have, in addition, access to features. So whenever you're in a state S, you also see the features corresponding to that state S. And this is a d-dimensional vector. And what's important about this is this promise that the V star is going to be exactly equal to the inner product of some hidden secret weight vector theta star and the features for the state. And notice that the features depend on the state, but the features are given to us. However, the theta star does not depend on the state. And that means there's only d parameters to learn, because these are d-dimensional vectors. And so that's the hope here is, you could have a lot of actions, even infinite. And if you didn't assume anything, you would have to kind of learn individually for all of them how to act in there. But here, instead of that, we condense all of that down into d parameters. If you learn these d parameters, you know V star, and you know how to act optimally. And the hope is that you can kind of like work in this MDP and figure out the d parameters in time that is polynomial in d. That's what we're shooting for, and we'll see if it's possible or not. Okay, a couple more things. Like there's also the Bellman optimality equations, which is just this recursive equation that the V star needs to equal, for the best possible action, the reward that you get, plus the expected next stage reward. And we're going to be using these Bellman equations a lot. So I just wanted to put that in here. Okay. Right. Okay. So you can see the local planning slide. Okay. Here I'm describing the kind of learning setup and how we interact with the MDP. With online RL, what you'd have, it would be a little bit less permissive than this. What you would have is you'd have this black environment, and then each of the states would be fed into an agent, and the agent would have to give you an action, which is then performed in this environment. And as I said, we're going to be a little bit more permissive here. We're going to allow, when instead of agent, we're going to call this thing a planner, and we're going to allow this planner, when it receives a state, to go ahead and do a little bit of planning in the background. And after it's done the planning, it will give us an action. And so what is this planning? This planning is basically, this planner can go ahead and consult a simulator by giving it queries of the form of a state and an action. And the simulator will it will have a perfect simulation of the world, and it will give you back, it will give the planner back a possible transition in the form of the next state and the reward and the features. So it will tell you what would have happened, what is one possibility of something that could have happened if you performed that action in that state. When we say local planning, what we mean is, in this case, you can only give it states and actions that you've seen so far. But in some cases, for negative results, we will allow the planner to have a look at all the states and all the features. And the negative results I'm going to present will be stronger that way, because they'll be able to see all of those and still will have a negative result. So that's just a little caveat there. But anyway, the point is, the planner will do some queries of this form, and at some point it will decide to stop and output an action. And the expected number of times that it queries this, the simulator, is called the query complexity. And that's going to be a central kind of quantity describing how good a planner is. So when it outputs an action, that action will be fed into this environment. and then performed, and then there's a next state, and that next state will be fed into the planner. And so this is kind of an interconnection of a planner and an environment, an MDP. And so when we use the planner in this form, the policy that we end up implementing is going to be called the induced policy of the planner. So every planner kind of implicitly defines a policy, which is the distribution, a probability distribution of actions that will be performed in this closed loop form. And then we can ask the question of how good is this planner in the form of how good is the policy that it implicitly defines. And that is basically just the value of the policy of the planner. So what we want is this value to be close to optimal. That is what we want from the planner, to be able to come up with actions that will give us a high reward and expectation. Okay, there is a little bit of a comparison here with model predictive control, where this illustration shows how to learn how to drive. It's kind of enough to plan only until, from the current state, only as far as the green line goes. You try to not crash, locally, and somehow you can put that together and drive, in an okay way globally as well. So that's kind of the idea of local planning. Why should you, plan everywhere and have to produce something that works everywhere if you could just look at where you are now and perform a little bit of computation there and then keep going that way? And so that's kind of the idea of local planning. Okay, here's the first slide with blocks. There's going to be a lot of these. What we want from the planner is we want generality. That means it should work with a lot of different kinds of MDPs. We want efficiency, which means it should have a low query complexity. And we also want effectiveness. That is, it should produce near optimal policies in terms of at least the value of the policy. So the crucial thing underpinning all of these is the assumptions that you make about the MDP. If you make assumptions that are too strong, you won't be able to apply this planner very generally. So you lose out on generality. You may be able to come up with an effective and efficient planner, but it won't be very general. Whereas if you don't assume, if you assume too little, maybe you're going to be quite general, but it might be impossible to come up with a planner that is both effective and efficient. And indeed, the recent results kind of carve out this cliff where if you assume enough, you will be able to have a planner that is polynomial in all the relevant parameters. But if you just assume a little bit less, just a tiny bit less, or you change a little bit of caveat somewhere, then right away you fall off this cliff, and it is provable that there isn't any planner out there, any algorithm that could solve this problem in an efficient and effective way. And so I just wanted to highlight a couple of these results that have very similar assumptions, but very different outcomes. And the green outcomes here are, planners that are polynomial in the relevant parameters, and the red results are the negative results, where we say, okay, there's a comment which, yes, sorry, but I'll just continue here. That I'm going to just address these couple of relevant pieces of work. The first one is if you assume that the Q pi, which is the action value function for a policy pi, if that is realizable for all policies pi, then that means, basically what we're saying here is if you take any policy and you take, with the same features, you will be able to find a theta for that policy, which makes it realizable. It's quite a strong assumption, but if you assume this and you're in planning, then you can use approximate policy iteration and an optimal design to come up with a planner that is polynomial in all the relevant parameters. However, this assumption is quite strong. Like it would say that the features would uniformly cover all the different Qs that you can get for all the policies. If we go a little bit further than this and try to have a weaker assumption and only assume that for the optimal policy, Q star is going to be linearly realizable, and you still have planning, then there's a negative result. And this says that no algorithm will be polynomial. One note here is that the number of actions is actually exponential, but the certainly the deep parameters you need to learn, despite all of this, you can't learn it in polynomial in the steps. And I'll talk about this result a little bit more. But it seems that if you add another assumption here, which is a minimum gap assumption, then things are possible again. And so what is this minimum gap assumption? It basically says that in any state, if you perform the optimal action, then the value of that is going to be at least some constant larger than if you make a mistake and perform any suboptimal action. That is to say, there aren't two actions that are very close together in terms of the value that you get for them. And if there is such a minimum gap assumption that it is at least some constant or some parameter, I guess, then you can use bootstrapping and you'll be polynomial. However, that is only the case again if you're in planning. If you take the same problem in the online setting, I believe it was maybe 3 weeks ago or 4 weeks ago, I don't quite remember, but there was a talk given about this exact setting, and where there's again a negative result. And then another assumption that you can make is you assume that Q star and V star, both of them, are realizable linearly. And if you have planning and the features are given in advance, then again you're going to be able to come up with a polynomial algorithm. However, if you are in the online setting and the features are given to you only locally, then again it's impossible to come up with such an algorithm. So that is where kind of we come in the picture. What we assume in this work is that V star is linearly realizable, and we add the extra assumption that the number of actions is small. So by small, I mean constant, like think 2 or 3, just a small number of actions. And if we have local planning with this, then we're going to be able to have an efficient and effective planner. And so this is kind of what the talk will be about, these kinds of assumptions here. Before I go into that, I just wanted to talk a little bit about how the minimum gap assumption works and why certain things fail if you don't have that. So if you have this minimum gap assumption, which is again like whenever you take a suboptimal action, you will lose out on at least some constant reward. Let's say that is a way to phrase it. If you have this assumption, then what you can do, and if you have a generative model, which is a planner setup where you can teleport to any state and perform any action, then what you can do is you can, and by the way, the features are given to you in advance. So what you can do is you can do the pre-computation of figuring out going to the last stage and figuring out which features are the most important here, which actions have associated features that span the whole space the best. And this is called an optimal design. So you can come up with a small set that like spans everything. And then you can basically try the states and actions for the corresponding, you can try the corresponding states and actions. And what you will find is you will learn the Q star for those kinds of features. And you will learn the Q star exactly because we're in the final stage, and the reward equals the Q star in that final stage. I seem to be having a little bit of technical issues here, but I mean, hopefully you can still see what's going on. I have indeed lost my slides.
We do see the slides.
No, I lost the so I was connected to another screen. Just 1 second. I'll try to connect back to it, and hopefully it will return, because I can't go on to the next slide.
Okay.
So this is a little bit annoying.
That's fine. Maybe in the meanwhile, if someone has a question, then
Yeah.
Any questions for the setup or?
Yes, on the previous slide, you were distinguishing between planning and local planning. So what is the difference between those? Planning requires you to output an entire policy. And local planning
so it's more that if you whether you're able to look for all the states and think of all the set of states and set of features in that state. If you get that whole set, that is what I meant by that kind of problem. But also
it's
I think
like global access, right?
Yeah. Global access. That is indeed what I meant. I think that would have been a little bit more precise. You know what? I'm going to open up this slide deck again, and I'll see if I can share my screen again, because I think this is irrecoverably lost now. So I'll say stop sharing, and I'll try this again. hopefully this will work. I love how it waits just enough to crash, and then oops. Okay. Okay, so where were we here? Okay, I'm back. Okay, I can't see you now anymore, but it's fine. Just shout if you need something. So where were we? What we were saying is you can look at the final stage, and you can look at the features there, and you can sort of get the most important ones and learn the Q stars there. And crucially, because of the minimum gap assumption, any difference between a good action and a bad action will result in at least some loss of value. So even if you don't learn the values, the Q star values exactly, just learning it approximately allows you to snap onto the optimal actions, right? Like you can always identify which action is optimal if you're, if you're not too inaccurate, because there's always a minimum gap between them. So you can identify the optimal actions exactly. And that's kind of the crucial bit. Whenever I see a minimum gap assumption being used, it's used in this kind of way of being able to snap, approximate learning to like exactly optimal actions. And so what you can do if you have that is you can go back by one stage and again, identify the most important features there and try them. And you can try them knowing that you know how to act optimally, exactly optimally, from the next state onwards. So then you can apply this sort of argument that you can always go back by one stage and learn about that stage because you know how to act optimally in the future stages. So that's kind of how this works. However, if you don't have this assumption, there is a big problem that tends to happen, and this happens to like this approximate dynamic programming kind of bootstrapping kind of algorithms that, and what I mean by that is these are algorithms that will learn a point estimate of a value in a stage, and then they'll go back to a previous stage, and they'll just use those targets use those S targets that you learned in the previous stage. Okay, I'll get rid of the dogs so you can concentrate. So basically what's happening here is if you learn that for the final stage, you learn the Q stars, because there's no minimum gap assumption, there's no snapping action happening now. And that means when you go back to a previous stage, if you learn about the Q star there by using the values that you learned in this capital H stage, then the targets, the values themselves that you're learning are going to be inaccurate themselves. And it turns out this blows up the error exponentially. So as you go, further towards the beginning of the episode, you will see that the error in terms of how well you can learn things is going to increase exponentially. Okay, and this kind of ties in with the negative result. I mean, the negative result says that no planner can solve this problem, even if it uses something other than what I just described about bootstrapping. And so what this is about is if you assume Q star realizability, then you have the following, but also I should say even this would apply to V star realizability as well. This isn't in the paper, but if you think, whenever you perform an action with a certain features, where the action A in a state S has some features, then the state you're going to get into is going to have the same features, and that is going to be the features of the V star. And this is the case because the construction here relies on a deterministic transition. So the point is this works for V star realizability as well. And the result is that any sound planner is basically a planner that works well, close to optimally for any MDP that satisfies the assumption of realizability. So any sound planner will have a worst case expected query complexity that's going to be at least exponential in at least the feature dimensionality D or the horizon of the problem capital H. And this is kind of bad, right? Because the hope was at the beginning that you reduce the number of parameters to D, and hopefully you can learn the parameters in polynomial time in D, and then you're done because you know Q star or you know V star and you know how to act optimally. Is everyone still with me, by the way? Because I can't.
Yes, absolutely.
But okay, everyone's with me. Okay. So that's a negative result, and I think that the reason why it's interesting is because it kind of highlights this fundamental problem with RL. I mean, RL is just very hard, and it is hard in ways that something like like bandits is not as hard, because if you have bandits and you have some sort of a low-dimensional linear structure such as this, there you can kind of do this optimal design business and figure out what things you want to try, and then observe the targets, and then calculate an average and have some sort of a statistical guarantee for that. Here, the targets are not really observed. Like the targets are Q star or V star, depending on the assumption. But you don't actually observe that. You only observe one transition. And to be able to know what the Q star or V star would have been, you would need to know how to act optimally from that point onwards. And this is kind of like a chicken and egg problem, because of course the whole problem is that you don't know how to act from that point onwards. You're trying to learn that whole thing at the same time. And so it turns out this is hard even if you can teleport to any state. So the context of this negative result is that this is where you see all the features in advance, and you see all the states, and you can teleport anywhere and query the simulator for any state and any action. And yet, and you can do any amount of computation, and yet you won't be able to solve the MDP because there isn't enough information revealed to you, because the Q star and the V star and these things aren't actually revealed to you. So this is kind of the crux of it. It is not hard because it's hard to get to an interesting state, right? It is hard because you could teleport to any state that you deem interesting. It is hard because, and by the way, that might be hard, how to get somewhere. But that's not why it's hard. It's hard because you just don't observe the targets, and what you observe has very low information. So here's the question then, like, if you don't observe these, then what do we actually observe? What is something that we can learn? And so this new method that I'm going to present will rely on a different kind of thing to learn. And this is going to be local consistency. And local consistency of the Bellman equation in particular. And the Bellman equation, let's say you have a policy pi, which is deterministic. That means for a state S, it will give you action A deterministically. And so what holds for this is that the value of this policy in a state S will be exactly equal to the reward that you get by performing this action, plus the expected value you will get from the next state onwards, right? This is just a fact. This equation holds. And so something about this equation will give you information. And so that's the whole, I guess this is like the most important part of this method is that this is what we're going to learn about, not the Q star or V star. Maybe indirectly we'll learn those too, but this is what the information that we're going to use is just this Bellman equation and the consistency of it. Okay, so I'll present the theorem now. There is this algorithm called tensorplan. This is a planner such that for any MDP feature map pair, when you have the realizability of the V star, and you have a bound, an L2 bound on the features, and also a bound on the hidden weight vector, which is going to be known to the planner, capital B. Then, with a number of queries that is polynomial in this quantity, tensorplan induces a delta optimal policy, which is to say the amount of reward, total reward that it's going to miss out on is going to be upper bounded by delta. So this polynomial, by the way, I mean, it has D and H and delta, as you would expect, but it does have the number of actions A in the exponent. So you might argue this is not a polynomial, but I argue it is a polynomial in the context of the action count being super low. So remember I mentioned that is the extra assumption we make. We only make it because of this. Like if you have 2 actions, then this isn't then this is a polynomial. Or if you have 3 actions, it is a polynomial. But very quickly, this will blow up. So this is a big caveat about this result that the A is in the exponent. There is a question of, is this necessary? And this is, as of yet, an open problem, but like we hope to be able to solve this soon, and it is looking that it is that it will be exponential in A necessarily. So another thing to note here is that this theorem can be strengthened a little bit in terms of the guarantee that it has. And if you consider all the policies that are deterministic and realizable with the features, that is to say, you're not just considering the optimal policy, and you're not just saying the optimal policy needs to be realizable. Maybe it isn't, but maybe some other policy is realizable. And as long as that policy is deterministic, tensorplan will come up with, it will induce a policy that will be able to compete with the best of these realizable deterministic policies. So it will be up to delta worse than the best of them. Also some extensions. One of them is that the results hold in the unrealizable case, where realizability holds approximately, but not exactly. And it also holds in the discounted setting for discounted MDPs. So it's not just the H horizon MDPs. Okay, I think maybe this would be a good time to ask whether there's any questions that we need to look into first, because now I'm going to describe what the tensorplan does, and if there's any burning questions, maybe I should take a little. Wow, it's a big fractal.
Yeah, that's very psychedelic, Gelért.
Yeah. Should I carry on?
Yes, it's all very clear, I think.
Okay.
Yeah,
Okay.
Maybe I'm going to ask about the previous slide. So where you say, where you had some S here in the second theorem. So how is S quantified? So S is the input to the algorithm.
So for realizability, when you have for realizability such as let me see. Actually, all the S's are in terms of, yeah, no, okay. So S is given to the planner. So this is actually the, you remember the planner looks like this. And so basically S is an input to the planner, and the task of the planner is to come up with an action which is good in S.
Right, I see. And then the guarantee says that,
And then by the way,
S,
then the next state will be fed into the planner as well, and the planner will be called for every single state along this this sort of episode. And this is this is the guarantees here. And so what the guarantees say, this is for all S. For all S, if you give S to the tensorplan, then it will give a good reward. And the way this is phrased is that the policy that the tensorplan induces, which is the policy that you get if you just give whichever state you're in, you give that to tensorplan, it will give you an action, you perform that action. If you execute this policy, then for each state, you'll be the value will be near optimal. Does that make sense?
Yeah, that does make sense. Yeah, maybe there. Yeah, it's.
So yeah,
over,
I guess the short answer is that this is a for all S
right.
in the state set. And by the way, this holds even if the set of states is infinite, and it holds exactly because tensorplan will always get whichever state is the input. So it will always.
Yeah, I guess what's sort of subtle about this is that the supremum over policies. If your set of policies does not include the optimal policy, then this is going to be achieved by a different policy in every state. And then I'm just wondering like what this guarantee actually means in the end. So like if I run this planning algorithm on the fly, then does this guarantee me any global guarantee on the sum of discounted rewards that I'm going to be getting or no? But that's probably a very technical question that we should discuss.
Yeah, no, I see the question. It's very interesting. I don't know if I can say anything off the top of my head on that, on how, but yes, you're right. It will give you the supremum for any state, and the feature policies themselves can be different indeed.
Yeah, I think this is very technical. Let's talk about this later.
Cool. Okay, I'll just carry on then.
Yes,
so to basically describe what tensorplan does is first I will say this is a generate and test kind of algorithm, and there is going to be an outer loop that chooses some theta that it hopes to be the real theta, and then it will do some sort of experiments to see if it's true or not, and if not, then it will just choose another theta and so on. And so throughout this, it will maintain a set of plausible thetas, which this is basically the shaded green region here. these are the thetas that that are consistent with the experience so far that it has gathered, right? So whenever we see that some theta cannot be, whenever we get enough evidence that some theta cannot be the real world model, the real parameter, then we can restrict this set to only include thetas that this evidence wouldn't rule out. And so in this way, we're shrinking this set of plausible thetas. And whenever we start a new iteration, we choose a theta plus for that iteration optimistically. And so what I mean by that is, whenever you choose a theta, you will basically see all the values. If that theta was true, then all the values would be just these inner products with the features. So you choose optimistically, and that means you look at the state that you are supposed to be doing the planning from, that is the input state S. You look at its feature, and you choose the theta plus that has the highest inner product with that. So basically, the theta plus that promises you the highest reward. And so you choose that. And by the way, this is the only piece of optimism in this algorithm. Everything else, as you will see, won't be optimistic about this. But this bit is where the optimism comes from. Okay, and so when it chooses, after it chooses a theta plus, it will start, gathering information about whether this could be the true parameter or not. And so what it does is it will execute this policy, that, basically characterized by this theta. And what this does is it tries to find an action which is consistent with the Bellman equation. And so what that means is it will try all the actions, and it will see whether this star equation holds for any of them. And if it does, it will take any action for which this holds. And so what this equation says is that the value predicted by this theta should be the same as the reward plus the expected next state value predicted by the theta. And so this must hold for the true theta, right? Because we are considering deterministic policies that are realizable. That means for an action, for the action that the policy chooses, this must hold. So if this doesn't hold for any action, then like we know this is evidence that this theta isn't right. But if it holds for some action, then we can just basically just perform that action. So in this case, we're checking two things, actually. One of them is whether the value that is predicted by the theta plus is achieved by the policy that I just described, which chooses consistent actions. And we check whether this consistency holds. But it turns out that the two are actually the same. And that is to say, if consistency holds, then you will get a guarantee. So B implies A. You will get a guarantee that the value predicted by theta plus is achieved by this policy. And why is that? It's because if you consider this equation, what it says that any reduction in the next state expected value compared to this state's expected value will have to be offset by the reward that you get. And so you can imagine that you could basically use a telescoping argument and do the same. If this consistency holds forever, then I can plug into here another equation like this. And in the end, I will end up with the value of the episode over, so value of capital H, which, when the episode is over, it is defined as 0. Like there's no more value to be gained because it's over, the episode is over. So that means at some point this term will disappear, and what you will have is just the sum of rewards. And because consistency held throughout, the value that is predicted is going to equal the sum of rewards that you actually end up gathering. So in this way, B implies A. So all you have to check is whether there is any consistent action in this sense.
Okay, wait.
And notice that we're not taking a maximum.
Confused here. So how is this pi of theta defined? Is it defined through a policy that is consistent, that picks an action such that this consistency condition holds?
Actually, the technical definition is it will take the action which minimizes the discrepancy here. So if there is a consistent action, it will take that action. If there isn't, it will take something that is the least, the most consistent, But the point is, well, if this happens, then it's basically a failure, and we will update our set of thetas. So we'll basically break out at that point. We'll say, this didn't work. But to give it a definition that actually is well defined, we'll say that it will minimize this discrepancy between the left and the right hand side.
I see. So basically, you just pick a theta plus, and then you check all the actions if this condition is satisfied. If there is such an action that this condition holds, then you say that you're good, then you proceed. If there's no such action, then you just say that, okay, this theta plus was bad, and this is definitely
exactly
what I'm looking for. And you only do this locally for the state where you're in, like at the input state to the planner.
Wait, can you say that last?
So do you only do this to the input state?
Oh no, you actually enroll entire episodes.
Okay.
You try to, because you want that. Because only then does the telescoping argument actually give you the sum of rewards along an episode. So you will basically play a couple of episodes with this policy, and if a lot of those episodes work out to be consistent, then you can have statistical guarantees that the value of this policy is actually really what is predicted, and then you're good. But if not, then you will fail. And so that's the idea.
All right. Okay. And then when checking this condition, I guess the challenge is that you cannot actually evaluate this expectation, and you need to draw like a bunch of samples.
Yeah. And you will, you will approximately evaluate it. But we'll get there soon, I guess.
All right. Okay. Yeah.
Because so far I'm just assuming that everything is equal and everything is nice, but actually there will be some approximation errors. But that will be a separate slide. So yeah, one thing I wanted to point out though is that we're not taking the action that maximizes the value according to this model, this theta. And then that's interesting. We're not trying to maximize. We're not trying to be optimistic here anymore. We were optimistic with the choice of theta plus, but here we take any action that is consistent, and that allows us to compete with policies that aren't the optimal policy. Like a policy might choose some suboptimal action, but if that's the best one that is realized with the features, then it will it will try to learn that one. So that's kind of interesting. It would strengthen the results that way. The only source of optimism coming from this first slide. Okay, so another thing is, which I didn't yet talk about, is what happens if we fail. Well, if we fail, we just update the set of thetas that we consider to be ones where all of these equations that we've seen so far would not have failed. So basically, we take a theta that in hindsight would have fulfilled all the requirements that we observed so far. And so we will choose, again, optimistically and carry on like that. And so with this kind of an argument, there's two questions. One of them is if it finishes and outputs some policy. Basically, if this works for a long time, it will output this policy with the theta plus. And if that is output, is it going to be a good policy? So that's the first question that we look into. And so first point is that you have this 2-in-1 kind of thing. Remember, like B implies A. So that means all you have to check is local consistency, and you will get the value guarantees for free. That is, the value will be close to what is predicted by the theta. And also, when it stops, it will have found some theta for which the value of this policy that it's been trying is in the span of the features. And also, because this theta was chosen optimistically, this value will have to be at least as large, or approximately at least as large, up to some approximation error, than the best possible. So this is how we can compete with any realizable deterministic policy. Okay, so this is the why is it a good policy part. And then the next question is, why does it stop? Like there's this iteration, this iteration here where you continuously shrink the set of thetas that you consider. Question is how many iterations, and does it ever stop? And so for this, let's look into what we're actually learning with each time step. And for this, consider that V pi for some policy pi is realizable with the features, and it is realizable with the hidden weight vector theta. And let's say that this deterministic policy will give you action A in state S. And so what we know is, because of the Bellman equation, this first line must hold. This is basically the local consistency line. This must hold. But because of our assumptions, we can just plug into these values. We can plug in inner products, right? With the features and the theta. So that is just using the assumption. And then in the third line, what we can do is we can concatenate the scalar R with the features that are d-dimensional. Basically, what we did here is we subtracted the left-hand side from the right-hand side. And then we have a scalar and we have some inner products. But we can put all of that into one inner product where we concatenate a scalar with some features, and then on the right-hand side also concatenate the scalar one with some features. And this inner product will equal 0. And we know this. So this looks good, right? Because this is a d+1 dimensional space, and it is some sort of an orthogonality result here. So you would think like maybe that reduces the dimensionality of the solution space by 1. But the problem is it doesn't, because we don't know which action would have been taken by pi of s. So we don't know A, right? I mean, if we knew A, we would kind of know, what to do already. So that's kind of, again, the same chicken and egg problem. We don't know A. But what we do know is that for one of the actions, this condition will hold. And so we can multiply. If we call this big thing just delta of S and A, then we can multiply all these inner products for each of the actions, right? And because one of them is 0, the multiplication of all of them is also 0. So this is the first part of this. And now we have some sort of an expression where we don't need to know anything that we don't know. Whenever we interact, we'll observe a condition like this, which must hold. And then the second part of this is that we can actually write a product of inner products as a big inner product of the tensor products of all the left-hand sides of the inner products and all the tensor products of the right-hand side of the inner product. So I'll say that again. These two quantities are the same. And what happens here is you take these left-hand sides and you take an A-fold tensor product of them, and you take the right-hand side and you take an A-fold tensor product. And these will be like two huge tensors. And if you consider these two tensors, if you flatten them and take an inner product, then that will be the same as the product of these inner products. And this is good because this quantity we know is 0. So this will give us an orthogonality result, kind of like in this case, we had an orthogonality here, but we just didn't know A. Here we don't need to know A because we product everything with all the actions. But what we know is this orthogonality holds. And this is orthogonality in a d+1 to the A-dimensional linear space. And so what tensorplan can do is basically it can check if this is orthogonal, if this is 0, then there will be a consistent action. So just take that action. But if it is not orthogonal, then it fails. That is the failure condition. And it can restrict the solution space to only consider thetas for which this orthogonality holds. And we know, like every time this happens, the solution space is reduced by 1 dimension. And so therefore, maximum d+1 to the A times can this happen. That's kind of the argument, except we didn't yet consider approximation error. So I'm going to talk about approximation error next, unless there's a burning question here.
No,
okay.
It's very clear.
What's that? Very
clear.
Okay, so recall the definition of this delta of S and A prime was this, like it has rewards, expected next state features, and so on and so forth. And we don't actually observe those. What we can observe is we can take a lot of these samples. We can take a lot of these queries where a lot of the different realizations of the rewards are given to us. We can take averages of those, and that will give us a tilde delta, which will be close to the delta. And so that will mean that this quantity here, this inner product, which used to be equal to 0, is now less than epsilon. For some epsilon that we can basically set, we can make this small, but it's never going to be 0. And we also know because of the reward boundedness, like every reward is bounded between 0 and 1, therefore all the values are bounded between 0 and h, capital H. And therefore, there's a constant which bounds all the different inner products as well. So if you take the product of all of these, then it will turn out to be at most capital H to the A times epsilon. And you can think of this as a small number because you can set epsilon to be like super, super small. That like offsets the capital H to the A. So this is a small number. It's not, again, it's not 0, but it's small. So the argument is a little bit modified. If this condition is satisfied, then there will be an almost consistent action, which, it's almost consistent. So there will be an extra error, but that extra error is actually controlled by epsilon. So it's small. We can set epsilon to small, and it's going to be near 0. And if it is not satisfied, then we restrict the solution space, and we restrict it according to this equation here. Basically, for all the tilde deltas that this has failed, we will only consider thetas for which all of these conditions are small. So that's the new solution space. So we restrict the solution space, and now the question is maximum how many times can we do that before we find the real theta necessarily. And because this isn't like equal to 0, like it's not like a super simple sort of linear algebra kind of argument, but instead we're going to use the eluder dimension kind of argument due to Rousseau and Von Roy. And this argument is, well, just let's simplify it. If you're given a set of possible functions, this is like a set of functions that you're given. And let's say the environment only has one. So there's a secret one function, and you're trying to find the values of that function everywhere. And the question is, how many points do you have to learn about? Do you have to learn the value? So like that secret function, you can learn its values by looking at some points. How many points do you have to look at it to be able to say its value everywhere? And so in this case, there's an illustration here. Let's say there's like, a set of possible functions. And we know that x1 is approximately this much, x2 is approximately this, x3, x4, this. If there are two functions in this set of functions which take roughly the same values so far, take wildly different values somewhere else, then you can add this x5 to your sequence. And you can grow this sequence, and every time you add a new value, there should be a function. There should be two functions in this function class that will agree with the values so far, approximately, but disagree with the new value. So basically, this is capturing this concept of how many values do you have to learn about before you learn the entire function. And this is called the eluder dimension. So the length of the longest sequence for which this is satisfied. And it turns out that the eluder dimension is very similar in this linear case to the actual dimension. And in this case, the dimension, instead of d plus 1 to the a, what we have here is order d to the a times a plus times some logarithmic terms. So it's very similar in a way. And so we use this kind of an argument to say that this red thing, this not satisfied thing, will only happen at most some number of times. Because every time this happens, we would have taken a theta that agreed with all the values so far, but disagrees with the real theta here. And that's the crucial bit. That's basically the same kind of argument as in the eluder dimension. OK. There are two extensions, which I don't know if I have time for. I think I'll just try to be reasonably fast here. So one extension is the near realizable case, where instead of this equality, so far we had equality here. Instead, let's say they are close to each other up to some eta. And what you can say here, all the results apply, basically, all the guarantees apply here as well. And this is because for any policy pi for which this is true, you can construct an alternative MDP M prime, where the only difference between this M prime and the original MDP M is that the rewards are in state S and stage H are shifted by this Z of S and H amount. And this is going to be, this quantity is carefully constructed in such a way that by definition, M prime will be exactly realizable with the same features. So this is just correcting for the eta error, by adding these rewards, these to the rewards. And so we knew that tensorplan had to be resilient to some measurement noise, and that was, basically the argument here, that you don't observe everything exactly. So here, if you think that you're getting a simulator about M prime, which will give you R plus Z, but you're actually just getting R, you should be resilient to that as long as the Z is small. So this is the idea here, that Z is going to be very small. is going to be an absolute value at most 2 eta, and this can be considered just noise. So tensorplan will hold, the guarantees with respect to m prime will hold, even if the simulator is simulating m. So this also covers the case where the simulator isn't perfect. The simulator will make some sort of a error as well itself. It's not a perfect simulator of the world, but the tensorplan guarantees still hold. So that means tensorplan is like almost optimal in m prime, and because m prime is so close to m, its values are also close. So that means it will also be almost optimal in m. And this is kind of the reduction style argument for this extension. And another extension is to the discounted case. Again, all the guarantees continue to hold. In the discounted case, instead of summing up age rewards, you have like a sum of a geometrically decreasing sort of sequence of reward now plus gamma times reward next state, and then plus gamma squared reward 2 in the future state, and so on, for which you can also write the Bellman equation, but it will be written in this way. So like it's going to be the expectation of the reward plus gamma times the next state. And so again, you can write the non-exact but near realizable case for this like this. And then it turns out a similar reduction kind of argument works. You can set capital H to be the effective horizon, beyond which the rewards don't really matter because they'll be multiplied by gamma to the h minus 1. So it's going to be tiny no matter what happens. And then you can create an H horizon MDP M prime, where the rewards and the features of a stage H are multiplied by gamma to the h minus 1. And if you think about it, it turns out that like any policy has a similar value in the original MDP M and this alternative H horizon M prime. And that's just because we like engineered into this the discounting. So that means like the value of the discounted MDP for each policy is close to the value in the H horizon, and therefore the tensorplan guarantees, of course, they hold for the H horizon problem. So it's going to be near optimal in M prime. Therefore, it is going to be near optimal in M2 because the values are all very similar. By the way, another point is this eta, a caveat here in the previous slide. I forgot to mention that eta has to be very small for this to work. So it's like, you can see how small, but the idea here is that you don't, like, not everything breaks as soon as you don't have equations anymore. So that's just a little caveat here. And then to finish this off, I want to just talk about a little implication of the positive and the negative result combined. And the negative result in this, what I'm talking about here is the Q star realizable, a lot of actions, and you get the features, and no planner exists that is efficient and effective. And as I said, it also holds for the V star realizability. So it seems that, at least if you have the V star realizability and local planning, certainly the features for many action MDPs are not very useful. You still have to do an exponential amount of queries to solve the MDP. But on the other hand, the features for small action MDPs are useful, as this tensorplan shows. So that should mean that if you can take any many action MDP and you can translate it into a small action MDP. Like if you have 100 actions, you just say, let's dial in those actions with binary choices. So you have like a deeper sort of sequence of choosing this action. But basically you can construct an MDP that works for all intents and purposes the same way as the many action MDP. And because knowing the features for the small action MDP would give you polynomial query complexity, but knowing the features for the many action MDP would still be exponential, therefore necessarily learning these features would be hard for the small action MDP. And it would be as hard as solving the MDP itself. And this is kind of interesting because so far we always assumed that you're given these features, and we didn't look too much. I mean, I didn't look too much into how these features are being learned or given. I guess the question is first, like, would they even be useful? But it's interesting to see that in the case of the small action MDP, these features are so much more informative. They carry so much more information. And this is because of the local consistency. It will hold for one action But if there is a small number of actions to choose from, that is a lot of info. TensorPlan is, that I should mention before I forget, is this optimistic choice of theta plus. We don't actually know how to do that in a computationally efficient way. So we're talking about just query complexity, the number of interactions with the MDP, with the simulator. We're not talking about computational complexity. So that's just another caveat to mention. Okay, I think, yeah, these are some references. I think this is what I wanted to say. So I'll take some questions now. Are we on time?
Yes, absolutely. Thank you very
Cool.
much. Thank you. So does, yeah, it's a little bit of virtual clapping. Right. So I don't know. Does anybody have any questions? There was a question that was actually answered during the talk by Amir Masood. Well, at least we touched on it, which is this update set of feasible thetas operation? Is this simple? Is this trivial? I mean, looking at the formulas, it doesn't look trivial to me at all. So in particular, yeah, that is this check. So like, is this a convex set in the end? So what do you know about this?
It's like it's some polynomial. What is it called now? Constraints. So it's not. Yeah, no, we don't know. This doesn't look very good. So this is the computational issue here. That it's kind of hard to maximize. What you're trying to do is you take this set and you try to maximize the inner product of something from this set with the features of the state that you want to do planning in. That's the optimistic choice, and it doesn't look very promising.
Right, and there's this product of this theta vectors, A times with itself, and that probably makes it a non-convex set.
Yeah.
Right.
Yeah.
I mean,
right, and also the maximum.
If you ask whether you can represent this compactly, you can represent it compactly. So in that sense, the update of the set is trivial because you just like collect this data and you updated the set. What's not trivial is the optimistic calculation, right? That needs to happen afterwards. And for that, it would be useful if that set was had some nice structure, but it's pretty ugly. You can also think about like doing everything in a higher dimensional space, and then you just have like lots of values to like an expanded version of this, but then you're over generating, and so that's not good either. So altogether, yeah, it's tricky.
Yeah, so I guess my biggest philosophical question here is regarding this product that seems to give all this trouble in the definition of this confidence set theta. So do you think that this taking the product of these values, is this like a fundamental operation? Is this the right thing to do, or have you considered other options as well?
Yeah, so I guess what I should mention here is that most of this applies, this kind of algorithm that works like this applies to cases. I'll answer this question in a little bit of a roundabout way, but the point is most of this applies to cases where you don't have linear function approximation. You just have some arbitrary function set. You need to just have a way to update your confidence set, right? Otherwise, it would apply if you just check local consistency. So the reason why we do this product is if you have this linear sort of structure, then a way to talk about how quickly this set shrinks is to multiply all these things and say that one of them is 0, so therefore close to 0, so you can use the eluder argument. So this is just a way to use the fact that this is a linear function class, and so that's why. So this is interchangeable if you like, in case you had a different function class. The idea is that you just take the set of functions among those that are consistent. That meaning that they always satisfy these local consistencies. Now, the question of if you have linear realizability and you have the linear structure, if there is anything better than the product to be taken, I guess this isn't entirely known yet. Like this is all the way going back to what I mentioned, that this a in the exponent. We don't know if that is strictly necessary. It seems that if you take these products, you will certainly get that a there. But I'm not very optimistic in terms of whether we can remove a from the exponent of any kind of upper bound.
So one relatively obvious possible improvement that I can see, but maybe that's wrong, is that you know that actually the optimal policy also satisfies an inequality constraint, right? You know that the optimal policy satisfies, v greater than Bellman operator times v, right?
Yes.
So would we be able to use this somehow?
That's a very good insight. I have been unable so far to use that efficiently. If you think about it, you basically get half spaces which either cut a lot or don't cut a lot, and it's kind of tricky. Whereas with the current arguments, you basically reduce the dimensionality by 1 every time. So that's where it's technically more difficult. But yes, there could possibly be something to be said about these inequalities, at least if you consider optimal actions only. It just so happened that we couldn't find anything valuable in those inequalities, and what we found to be very valuable is just these equalities.
Also, for the optimality constraint, there's something funny about it, particularly when you use it with optimism, right? Because if you think about, I guess Gergel is thinking about something like v less than tv as appears, and the primal of LP for MDP, and in this case, you actually get the upper convex hull of V star, right? And in the original primal, you have to add a main over V to actually get V star. Actually, otherwise you get something quite meaningless, right? So you can be, for example, you get at one level you can be this high, and then X level, you can just boost up V to arbitrarily high number, and that will always be satisfied. But then if you do main over V, then you can do optimistic at V at the same time. So there's a little bit of clash of that. So whenever you use one-sided constraints, inequality constraints, you have to be very careful and find a way to impose tightness by some other means. So it's just a little bit unclear when you do for V less than TV specifically, how do you impose tightness?
Yeah, right. Yeah, so I was just thinking that maybe this could be an obvious way to eliminate huge numbers of thetas very quickly early on, but yeah, it's not so obvious at all. Yeah. Even after this very short discussion, I can see that.
I think I missed the part about the eluder dimension and also the approximation. I just zoned out. I was wondering if you could go over that, so I just kind of know what's going on there. Yeah.
Sure. Okay. I guess just the gist is that this slide just said that if you could see these deltas exactly, then this equality would hold exactly. These deltas with the expected reward, expected next state, and features, and so on. But you don't observe those exactly. You can take some queries and you can take averages, but you will only observe this tilde delta, which is close to, it's the average reward is close to the real reward. The average expectation here is close to the real one. And therefore, because you only observe that, you don't have equality 0, you have less than equal epsilon. And then you can bound the rest of the actions as well because of the value bounds. And then and then you have this constraint. And then here's where the eluder dimension comes in, is basically every time this is not satisfied, you will have another case where there are two functions in the possible function in this function class of all the value functions that are realizable with the theta. You have two of them that agreed so far but disagree now. Right, because now, the real theta will be small, in terms of it has to be locally consistent, but the theta that you have now is large because it's not consistent. So in this case, you have another point where things disagree, but everything before agreed. So that's the same thing as the eluder dimension, which just accounts.
I see. But so this tensor has no structure, right? I should just think of it as a vector of d to the a.
Exactly, d plus 1 to the
Okay.
a, yes.
D plus 1 to a. Okay. So it's just like linear, actually.
Exactly.
Yeah, it's just the linear. So Jason, also, you're probably familiar with like, using ellipsoid potential to analyze this. There's an alternative proof that gives you the same result, just using standard linear ellipsoid works the same. So there's nothing fancy here. It's
and
just
this
a
isn't approximation error in the sense of misspecified. This is error because of finite queries to simulator.
Yes, but also this is where you can plug in the approximation error into the same thing.
In this, you handle in the same way. Okay.
Yeah, so you just exactly.
Got it. Okay. Right, estimation error. Yeah.
Exactly. Yeah.
Cool.
Okay,
And
okay, no, sorry, just.
I just wanted to, if you didn't have this estimation error, so if you could compute these estimate in these expectations exactly, then would you be able to solve this efficiently, or?
Oh yes. There's this paper called optimistic constraint propagation. Basically, the reason why you can solve things way quicker, polynomial in D, and you don't need the action and the exponent, I believe, is because in the final stage, when you make so all the way back to this minimum gap sort of assumption here, it's like having a minimum gap assumption, right? Because you observe the final stage towards exactly, right? I guess it's not exactly like a minimum gap assumption, of course, but because you observe these exactly, they will somehow give you they will give you exact constraints and reduce the dimensionality by 1 of the d-dimensional space. Does that make sense? Like, I'm not sure if I'm explaining this right.
Yeah, I guess you can eliminate more efficiently the possibilities.
Certainly because of the final stage, right? If you look at the final stage, if you take an action, you will observe its value. So if you imagine Q-star realizability, right? Then this would mean that I guess then the argument is easier. If you have Q-star realizability and you observe the value exactly, then you will observe literally what you observe is an inner product with the theta. So as long as you take linearly independent features, if you take d many of them, then you're done, right? And you know exactly what theta is because it's going to be it's going to specify theta exactly. So the kind of the trouble happens when these features are actually just small and then overwhelms the information that you get. And it seems there seems to be like this big separation, right, between this second line sort of negative results and the same case where you have deterministic MDPs, for which that paper applies. When you have Q-star realizability and exact, everything is exact because everything is deterministic.
Thanks.
So regarding something that you mentioned earlier, that when we roll out the policy, we always check consistency. I forgot, did we think about what happens when you do max over there? I thought that it might also work.
When we do max here?
Right.
Is that what you mean?
Yeah, when you roll out, like let's say you figure out a theta, and when you roll it out, and then there's a related thing is that an opportunity to, maybe I'm just asking stupid questions, but is that an opportunity to get, say, if we're actually realizing a pi that is not pi star, you can imagine doing something like that. Like if the theta is actually like, representing v pi, then if you take a max, you get automatically 1-step improvement, right? Are we missing out on that opportunity, or for some reason max just doesn't work here?
Yeah, so what I think about that is certainly when you're checking for consistency, if you took the max, that would be like, then you wouldn't be able to compete with anything that isn't the optimal policy, because that for the max action, this doesn't necessarily have to be satisfied.
Right, but I'm saying but they can do consistency and rollouts like
exactly. So
right?
what? I understand the question. The question is, what if you take that as your consistency check, but actually when you unroll,
right, you take max.
And so the flip side of this is if you unroll a different kind of policy than what you checked consistency for, then you don't have this B implies A kind of thing, right? Because the reason why we can have a guarantee about the value of the policy is because if the consistency holds, then the value has to be good. But actually, if you take the max action, I don't know if we have any guarantees that you can use that the value.
But the thing is that I'm taking max, but I'm still, I will still call it a break if there isn't any action that is consistent.
I see. Now, okay,
right?
that sounds, and
then whenever I take an action, I'm taking an action that presumably sends me to some better place. Right? And there's always an action even later on to maintain that value. But again, I'm choosing something even better. And
no, I think this could work and give you.
Yeah, Sims could work, but there's also some triviality is like, if you really have a good policy, I mean, you can always invest a few more steps of planning to get a maybe improvement. But what I'm guessing is that can we essentially get that without additional levels of simulation?
I see. This is a very good idea. I think it might work because you would basically be. I guess the final guarantee would still be that you're at least as good as the best linearly realizable policy, right? But
you can precisely define its one-step improvement as in policy erasure, right? And try to, I'm not sure, but I think the best case scenario is that maybe you can compete with that. Because we're doing this in a very local manner, right? Whatever state we encounter in, we can do this thing. So that's kind of like L infinity sort of, we're improving over that policy everywhere. Or maybe there's a caveat that we didn't notice, but
yeah, I wonder what happens if you take a max action and no, actually, I need to think about this a little more, I guess, before.
Right, because if you take a max action, you will be throwing into like the very different states. But our procedure, the first step of our procedure, will take care of that and eliminates, do the proper version space shrinking, whatever states that you're going to visit.
Yes.
So I don't think that's a problem.
Yes.
Yeah.
I'll think about this. Yep.
Too late to add to the paper, I guess.
Yeah, I guess. The
archive. Yeah.
Yeah, I guess these questions are getting very technical now, so maybe we can stop recording. I guess that would make sense. Oh, nice. All right. Okay, so anybody else with crazy technical questions?
How do you consider all of this in online settings?
Yeah, so if you have like a completely online setting, then if you don't even have a one-step look ahead, then the V-star won't actually help you at all because you won't be able to identify the action. I can just scramble up the actions, right? And you don't know which action takes you to which next state. So if you don't have any sort of one-step look ahead like this, then you can't do anything, even if you knew V-star. So that immediately kills the setting. If you have a one-step look ahead, but otherwise you need to be online, I guess what I think you could translate this into is if you just do what tensorplan would wait, hold on, let me actually think about this for a second. Right, no, because so if you're always going to restart the episode from the same state, then it seems you could just give the action that tensorplan would want to simulate next, and you would be able to maybe come up with a sort of a regret guarantee, that over time this will converge towards some optimal policy, and therefore the regret will scale such and such way. So I think it is there is some promise in translating this to that. Certainly, without a one-step look ahead, there's nothing you can do. But even otherwise, like, it's not going to be optimal immediately, and of course we can't expect it to be, because it couldn't even see the things that would happen later. But I think what it does, it will do unrolls, and it will do unrolls from the starting state. So if your setting allows for that to happen, and in fact if it's important, if there needs to be some memory shared between different iterations of this online sort of algorithm. So if you have that, then I don't see why you couldn't just use tensorplan like that. That's my initial sort of thinking. But of course I need to think about it. Yeah.
Yep, and I think so. If we trust have some local consistency, as you mentioned, with respect to the bootstrapping, or how we get our model, that will also have an effect upon the if we look at the planning trajectories in the end, depending on it definitely will. Thanks.
Wait, sorry, I didn't catch that question.
I was just on tangent, thinking about how bootstrapping might affect some sort of initial online routine with respect to the collection of the data, and trying to kind of like expand this into truly how do I say it, V-star or without V-star. That's I was thinking in those terms about how those inefficiencies might draw on the online settings. Maybe we can discuss that later. I will have to.
Yes. Let's discuss that later. But I think what I can say now is, like, certainly, like, if you just take point estimates of, if that's what you mean by bootstrapping, I mean, that's what I meant in this talk about bootstrapping, is like, take a point estimate of what your Q star or V star is in each case. Even if you have a more permissive setting, such as planning, what you will find is these kinds of things don't work. At least they don't work if you have a lot of actions. We don't know if there's a construction that has a lower number of actions. So anything that does work needs to use that this has a low number of actions. I'm not sure if there is, if you're just going to use a point estimate rather than a local consistency, like, I'm not sure how that learning would be done. But certainly if you have an online setting, that's only going to make it more challenging. So that's something to think about.
Thanks.
So I have a question regarding it's V-star realizability and Q-star realizability. So, like, which one do you think of these is more natural? And in particular, why do you think it's natural to approximate optimal value functions? Because the more I think about it, the less natural it seems. But maybe
I think something here is, like, first of all, it's very interesting that that there are these, like, different settings where, like, there is actually a huge difference between the two assumptions that you would think should be related very very strongly. But I think in terms of what's more natural is, you can kind of imagine, we don't know how hard these features are to get, but you could imagine that, like, to get a feature for each state is going to be easier than to be able to evaluate how good a state is, to be easier than to evaluate combinations of states and actions for each state and action. Like, it just sort of amount of information wise, it means that features for all states and actions, that is the Q star features, would have a lot more information, or at least it's a lot more content to come up with if you want to come up with the features. I don't know how much this intuition holds in practice with the results that we've seen so far. Certainly, some of the results seem to be seem to only prefer one rather than the other assumption, and so it's I guess whichever will end up being more interesting or more useful, but it's the jury is still out, I would say. And certainly the as I said before, the V-star you can't use unless you have the one-step look ahead. So that's something to note. You know, are you in planning? If you're not, like if you can't use that, then maybe you shouldn't use V-star at all. Otherwise, maybe yeah. I mean, I don't know. I think your guess is as good as mine here, to be honest.
Yeah. So I guess what I'm wondering about is, do any of these arguments that you described today work for Q star as well? So if you have Q star realizability, can you adapt this algorithm to that setup?
Yeah, so it seems to be a little bit tricky. And what the reason for that is, if you look at the consistency thing here, we can actually measure the expected next state features. Like that's what the delta is measuring, is expected next state features minus the current features. But the point is you can measure this expectation. Whereas if you have Q star, what you want to measure is the expectation of some sort of a max taken inside the expectation, because you always want to take the best action and its features and then take the expectation like that. So what seems to be challenging is that you have a max inside an expectation, and that kind of breaks this thing where you can just take averages, right? Like you have for every and have statistical guarantees for that, because for every single time you want to take another sample to put in your average, you have to figure out which of the features is going to be maximal, and that just kills it. So
right, and then what you have is no longer linear in theta.
Exactly. So I don't know how to solve that. So that said, if you have a Q star assumption, but the transitions are deterministic, then this isn't the problem, right? Because you just take, well, actually, hold on. I mean, in that case, you could maybe do something, because it's always going to be the same states. So maybe it's not like trivial, but it's not going to be as hard as with the stochastic transitions. Certainly, it seems that for the negative result here, the construction used deterministic transitions. So like maybe if there's a proof that the deterministic transitions, you can always assume it and it will never be harder, never be easier, then maybe you can do something. So there might be a way around this, but not that I can see clearly yet. So
I thought linear Q star with deterministic dynamics was solvable. Isn't
isn't that the OCP paper?
Yeah, it's Zhen Wen and
yeah, but in this case the rewards can be stochastic, but the transitions have to be deterministic. Right. I don't know how. I guess this is a bit of a corner case, but yeah, thanks for.
No, but not even reward, right? There is also initial state that you must have a deterministic initial state.
Oh yeah.
I thought.
Wait.
But
I'm confused again. If the dynamics are deterministic, so reward is stochastic, I just play the same thing average and it should eventually kill the variance.
No, there is the combinatoric stuff, like choosing the right actions.
Yeah.
And,
but that's only like.
And that combinatorics totally breaks down if you have noise and errors.
Wait, hold on. If you have deterministic transitions.
Yeah.
And isn't it always just a consistency where one of the A have to hold? Like you always, what you do is like you play all the actions and you observe. No, actually, you take one action. You take a state and an action, and the consistency is going to be the next state's features. You know, one of them has to be optimal, and whenever you take that state in action, it's going to be the same features in the next state. So I think you again have like 8 different equations. One of them has to hold. I think so. I think if you have deterministic transitions but stochastic rewards, then you can adapt this setting to it.
I'm not. I feel like too. I'm not an expert, but I feel like okay. I'm not. It's possible you need a gap though, right? Maybe Q star with 0 gap, but stochastic reward, the averaging won't save you. I feel like with gap for sure, you're okay.
I don't
I
yet
think
see.
So we know that
What?
if we have many actions, then this won't work because
Oh.
the lower bound is actually of that type, and you have
Yeah,
deterministic
sure. I'm just
transitions
talking about.
and
I'm just
stochastic
talking about.
rewards. And I suspect that like you can always kind of like, if you have like if you allow stochastic rewards, okay, if you had I don't know, like whether you can transform the deterministic transition into stochastic transition. Kind of the hardness can be like whenever I construct lower bounds, I can push usually the hardness to the stochastic rewards. Like it seemed to be the case every time that we never had a problem with just like sticking with deterministic transitions and just relying on the stochasticity of the rewards, because sort of the errors blow up anyways. That's the whole argument usually. Maybe there is some case, actually we do have open problems, right? So Q star realizability, few actions, who knows, right?
Yeah. So if you can prove that deterministic transitions will never help you, I think if you have the stochastic transitions won't help you. If you have deterministic transitions, then I think you should be able to adapt this to it. And then the question is, what if you have all the stochasticity you want? And like you said, like if you can somehow prove that like you won't ever gain any hardness from having that stochasticity, then this could be an avenue to prove the Q star low action case. But again, like this is an open problem as you said. So yeah.
Wait, so for Q star, so if I understand correctly, or maybe this is just what I'm imagining, if you have Q star and deterministic dynamics, what you can imagine doing similar to this is that, so in this case, you run into a state, not a state where things get violated, but you run into a state action where things get violated,
exactly.
right?
Yes.
And
yes,
you want
exactly.
to say there's consistency, right? So QSA is equal to R plus max. You replace that max over A prime with this product of dot products, right? So you just assert that there exists one of those next actions, A prime, such that SA is consistent. SARS prime A prime is consistent under this Q, right?
Yeah.
And then you probably do exactly the same thing as we did here. And in this case, you'll be able to handle stochastic rewards, random initial state, and so on and so forth.
Yes.
But
exactly.
you still pay power to the A because it's the same kind of proof.
I think the only thing I'm not sure about is how do you which action do you perform in the very beginning? Because like obviously if there is then an action which is going to be consistent.
No, but no, wait. Don't you just do the same? You do optimistic, you roll a policy, and somewhere things are going to go wrong.
Oh yeah,
you look at which state action pair where things go wrong instead of like which state things go wrong, right?
I guess the first action is going to be whatever gives you the highest inner product, and then whenever you just follow the consistent action, or
or you do
or even what you said before, like maybe it's okay to just take a max there and you get even a better.
Or right. I think there should be a reasonable way to do that.
Yep.
Right.
Can you kind of like review the complexity of the theta plus? I think so. Here we are choosing it optimistically.
Yes. So the complexity for the computational complexity for making that choice.
Yep.
Yeah. So that's I think I talked about that a little bit before, that we don't know how to do that computationally efficiently because this doesn't seem to be a convex optimization problem. So the bounds, the polynomial bounds, are on the query complexity. the computational complexity of that choice is actually, we don't know how to do it efficiently. So that's one of the big caveats here.
Cool. But I think so. If if I go back to the initialization process, there the way I think so, the initial assumption was with respect to the bootstrapping, or the laying down of the MDPs. There we have some assumptions. Can't we? I guess my query is, can't we kind of like derive it from there?
I guess what we have, like the optimization problem, is in the landscape is in the set of thetas that satisfy the local consistencies. So that's this set, which is this is a very like non-convex set. And like maybe there is a better way to constrain this set that might lead to a convex optimization problem, but I'm just not seeing it. So like, maybe there is a better way to be constraining these sets. But certainly, if you do it this way, by constraining it to have satisfied in hindsight all the local consistencies that you have observed so far, if you do it that way, then it will be non-convex. So
okay,
that seems to be the issue. And then this is kind of the set in which you want to optimize, and this has a lot of these constraints here, which are polynomial.
Cool. Thanks.
I mean, it's linear in this D+1 to the A-dimensional space, but it's kind of, it's the same thing as saying that it's polynomial in the D-dimensional.
I wanted to ask, is there ever a setting where this tensor has more structure? It's not like all tensors. For example, it's low rank or somehow a polynomial system.
Yeah, so
like a variety instead of a linear.
I think for that, if we go back to this problem, which is, I mean, this is a pure mathsy way of phrasing it, but this is basically what's happening. Like you have, what do we have here? Like we have linear independence, and it's kind of the same concept. Like there's this, I believe this by phrasing this question this way, I don't think we're losing out on the generality of the setup, and certainly the solution to this will help. If you calculate it exactly, it will maybe not be d squared, but it will be d squared over 2 or something like that. The dimensionality of symmetric squared matrices. So it's like d times d plus 1 over 2, right? And so yeah, like we're maybe losing a constant factor, but I don't think we're losing much more. So
Csaba sent a message. He's saying that they're rank D tensors, so they're order A, right? The order is A.
How do I click on?
It's like this in-column message thing.
Oh yeah. No, it's just my computer is super slow. Wow.
I'm trying to think. So it's rank D. It's in dimension D. It's also rank D of order A.
Right. Yeah. No, I guess.
No, wait. Then that's weird, because then how many parameters do you have? Then you only have d squared parameters. D squared times A.
So I guess we only have d parameters, right? Because the theta only has d parameters. But I think the question is more like, how many times can you fail? And that is where you get the tensor, and that is where you get the full dimensionality. Not the full dimensionality, but up to some constant factor. You basically get most of the dimensionality of the tensor, because
I'm wondering. Basically, I guess my motivation was, is d to the a tight? Like, are there d factors that can be improved? We had some submissions, or they're going to be on archive, like basically about tensors and MDPs and bandits, where like eluder dimension wasn't able to leverage like this algebraic variety structure, but other smarter algorithms are. I was wondering if there's any hope to use those algorithms in this setting. Very high level.
Yeah,
I'll send you our preprint, but
I think in this case, I'm not familiar with this line of work. I mean, I would love to hear about. Do you have like
I'll
a
ping
reference?
You,
Yeah, that'd be great.
I'll ping you. I'll send you a reference. Yeah.
Because I'm just, I guess I need
think
to.
I don't understand yours well enough. It just looked like a tensor and maybe with structure to me.
Yeah, like I think certainly with the solution to this problem suggests that what we have, at least the way we phrase it, is near tight.
Okay, yeah, because that one makes it look like a subspace or something.
Yeah, like this is like when you constrain the solution set, and even though the solution set is d-dimensional, but you don't always constrain by one more dimension. So no, but I would certainly be interested in that line of work that you refer to. So if you can, I don't know if it's public, if you can paste it.
It should be on archive in a day or two.
Oh, okay.
It's
If you remember, you can just.
I'll send it to you. I'll find your email. Yeah.
Cool. Thanks.
All right, that's very good. I guess many of us have to leave, at least I certainly do. So thanks everybody for coming. And actually, we do have seminars in the upcoming weeks, which are not yet on the website, but next week we're coming back. We're going to take a break for ICML, and then we have a couple more talks lined up. So this is not the last time that we're seeing each other for the summer. All right, so see you all next week. Thanks everybody.
Thanks. Bye.
Thanks.
And thank you, Gelrt. Yes.
Thank you. Bye.
Thanks a lot.
Soccer time. Bye.